Now that we have all the technical jargon of how you form each of these leads with the negative and positives and whatnot, we can actually go to look at what each deflection of the EKG means and how what deflection means if you're looking at the atrium depolarizing or the ventricle depolarizing or the ventricle repolarizing. Just what the EKG actually means. And this is just electrical stimulation going through the heart, or a look at the electrical stimulation so we can see what it looks like on paper. Now, if it's a stronger stimulation, it'll be a stronger peak. If it's a low stimulation, it'll be a lower peak. You'll see once we show a picture. It's just like anything in the body where it has electrical stimulations to contract, it's the same thing with the heart. And this is a way physicians and whatnot can see what it looks like on paper. Now, the EKG tells nothing about mechanical efficiency or how well the heart is beating, how strong it is beating. It just tells the electrical stimulation. But luckily, most heart conditions lead to a different electrical stimulation that we can identify, like heart attacks, atrial enlargement, or hypertrophy. So we can see these different conditions on EKG. So this is a basic 12-lead EKG. As you can see, each peak measured means a different thing. Whereas a straight line means there's no electrical current in the heart, so the heart is technically not beating. And this peak is called the P wave. And the P wave measures electrical or the atrial depolarization. And I'll show a better picture to show this later. But the P wave is atrial depolarization. Because if you remember, the SA node is in the, here you go guys, a very simple version of the heart again. SA node is over here. This is the right atrium, and then the SA node conducts a signal automatically every 60 to 100 beats per minute. So a signal conducts and it goes down here to the middle. Well, when it does that, it passes the atrium, the right atrium, and thus that's when the atrium contracts when the signal passes it. Just like anything in the heart, when action potential passes something, that's when it causes contraction. So it's the same thing here. The action potential passes the right atrium and it causes contraction of the atrium. Now if you zoom in on the P wave, you can split it to two things. The right side is the right atrium contracting, because the SA node starts in the right atrium, so the right atrium contracts first. The other side is the left atrium contracting. Now this is the left atrium. There is a bundle to bring the impulse over here, and thus the left atrium will contract. Because the right atrium and the left atrium both have to contract because we went over the blood through the heart, it has to contract. Now what this means is, as you can see from this diagram, it's showing that the right atrium is contracting like maybe a split second before the left atrium. Now they're technically contracting around like close to the same time. And that gets very confusing because you have to remember, when there's blood in the right atrium, there's blood in the left atrium because the whole circle is a loop. So it gets very confusing. But essentially the right atrium contracts first and the left atrium contracts. And then they look like, then the contraction shows it on the P wave. This is just atrial contraction. And then you have a little pause, and we'll go over what that pause is. And then you have this, which is the QRS segment. We'll switch to green. The QRS segment. the QRS interval, sorry. QRS complex. Okay, so the QRS complex is ventricular contraction. Ventricular contraction. Going back to our square. Starts over here, you got the P wave right here, because the atrium contracting, and also the other side, the atrium. And then down here, it splits into the bundle branches, going to the Purkinje fibers, and wraps around the heart. And the left ventricle pumps blood throughout the whole body, so that's why it's so damn strong. It's such a high peak, because it's such a high voltage. Because the left ventricle contracts very strong to pump blood throughout the whole body. So this is ventricular contraction. The right ventricle also contracts really, but no one cares about that, because it's only bringing blood to the lungs. And then you have a little pause again, which we'll explain, and this is called the T wave. T wave. The T wave is ventricular repolarization. So if you recall from anatomy, when something depolarizes, it has to repolarize, and that's it's changing back to a negative membrane potential of -70. So then it repolarizes, and the ventricle repolarizes, and thus the T wave. Now you're probably asking, where is atrial repolarization? Because the atrium also contracts right here, so it should repolarize also, and it does repolarize. But atrial repolarization is hidden in this QRS segment, or QRS complex. But since no one really cares also, it's so small that we don't really focus on it. But it is hidden in the QRS complex. So that's the basic of, you got the P wave, which is atrial contraction. And I'll go over what each of these little humps mean. And then you have the T wave. Now the P wave is right atrium contracting right here. Then you have the left atrium contracting, QRS segment, and then the T wave, or ventricular repolarization. Now these different parts of the Q wave, or the QRS complex, this is called the Q wave. This is the R wave. And this is the S wave. Now, the naming convention of the QRS gets a little confusing. The Q wave is the first deflection before an R wave. It's always called the Q wave. So there might not be a Q wave, it might just be an R wave and an S wave. The R wave is the first upward deflection. Q is the first downward deflection. Now the Q wave, when it is there, recognizes the depolarization of that septum, which separates the heart. So like here, this is the septum, the wall right here. And normally you don't always see a depolarization, but if you do, that's a Q wave. R wave is first upward, S wave is the second. S wave is the first downward deflection that follows an R wave, or an upward deflection. So I will go over the book just on the naming convention, but the naming convention gets a little confusing for the QRS. Now what these pauses are, now when it comes to naming the thing, identifying things on a QRS, on a EKG, they can be called two different things in nomenclature. They can be called segments or intervals. Now segments are pretty much flat lines. So like this would be a segment, this would be a segment. Segments are when there's no deflections happening. So this will be called the ST segment. ST segment. Reason being because it goes from the end of the S wave to the beginning of the T wave. And this is called the PR segment, because it's going from the end of the P wave to the beginning of the R wave. Well, technically the beginning of the S wave, but the Q wave, but just forget about that. So it's the PR segment and the ST segment. Now the ST segment, I really don't have a definition for. It's just a flat line following ventricular depolarization and ventricular repolarization. Now the PR segment, there is an explanation for it that you have to know. So we'll just clear everything. So this is the basic heart. You have the SA node right here, puts an impulse, stops right here. Remember from the electrical stimulation video, this is the AV node. Goes down the bundle branches right here, splits into the Purkinje fibers, and reaches the rest of the heart. Now, so this is the SA node, AV node. Now the SA node is autorhythmic. It makes its own impulse every 60 to 100 beats per minute. So it makes its own impulse. The impulse travels down to the AV node, and then the P wave, atrial depolarizes, atrial contracts, pushes blood down into the right ventricle. Now, the reason why there's a little pause after the PRS, or there's a little pause right here, is because once the signal reaches the AV node actually stops the signal for a split second. So it stops the signal for about 0.1 seconds. It's a very split second, but it's very important why it stops it. The reason it stops the signal is to allow the blood flow to catch up, because the signal, electrical stimulation, moves faster than the blood. Electricity moves faster than a liquid. It's obvious. So while the signal moves down to the AV node, the blood is slightly behind it. So once the signal moves past the right atrium contracts, and it pushes the blood down, and it pushes all the blood down to here. Blood normally just passively falls into the right ventricle, but when the atrium contracts, it's called the atrial kick. It pushes any extra blood in here down into the ventricles, but it has to contract in order to do that. And now if there was no pause at the AV node and the signal just moved on, all the blood that was in the atrium wouldn't have fell into the ventricles, because the atrium wouldn't have time to contract before the ventricle contract, because the signal moves so fast, if that makes sense. So the AV node stops the signal for a split second, 0.1 second, so the rest of the blood can continue falling into the ventricle. And then the AV node lets the signal go, and the signal just zips on through the heart and causes contraction. It goes to the lungs, and it goes out through the body. But that split second is what causes this PR segment. And then we'll talk about different conditions where this segment is actually longer. That's what a bundle branch is. I'm sure by the arrhythmia you've heard about it. But a bundle branch actually causes the signal to stop at more than a 0.1 second. But in a normal individual, it stops in 0.1 second. In a normal heart that doesn't exercise, it stops in 0.1 second in order to allow the blood flow to fall into the right atrium or the right ventricle. So that explains what the PR segment is. The ST segment is just a line. There's really nothing about it. And now, so you have the P wave, the QRS, and the S and the T wave. And they measure different parts of the heart. And now going back to just the plain heart. Now, the P wave measures atrial depolarization. QRS measures ventricular depolarization, where the ventricle is contracting. This measures ventricular repolarization, or the ventricle is repolarizing. And atrial repolarization is hidden somewhere in this QRS segment. Now, for EKGs, as you notice so we'll just put a 12-lead EKG. This is a 12-lead EKG. And this is looking at every single nook, cranny, variation, every single part of the heart you can possibly look at. And you have, of course, this is lead 1, this is lead 2, this is lead 3, AVR, AVL, AV. Well, that's AVR actually. And then you have your chest leads, which are also called prechoral leads, V1, V2, V3, V4, V5, V6. Now, these leads, if you notice, some are negative, have some negative deflections. Like here, you have I can't zoom in more, but this is a normal QRS. This is a big QRS because you have a huge Q wave. A huge R wave. And if you notice over here, these are negative. These are negative also. And you got negative over here, negative over here. It's actually a transition zone. Now you're probably wondering why some things are negative, some are positive. It just depends on what lead you're looking at in the heart. Now when looking at electrical stimulation, actually I'll put this in another video since this video is already 10 minutes. But that's the basic, the P wave, pause, QRS, and then the T wave going up. It's very important to note that you have the right atrium and the left atrium. So different ones contract at different times. And then this is the Q wave, first downward deflection before the R wave, S wave, T wave. So it's very important to know which one stands for what depolarization, which one stands for what repolarization. Remember, this is ventricular depolarization. Depolarization means the same thing as contraction. So if she uses a different word, don't let it confuse you. This is ventricular contraction or ventricular repolarization, mean the same thing. This is atrial depolarization or atrial contraction. This is ventricular repolarization. Okay, so now in the next video, I'll just go over with the negative deflections and the positive deflections and how you know which one's positive and which one's negative.